So designs and economics of hydrogen energy systems. Here we explore how the components of a hydrogen energy system, production plant, transmission, distribution system, and refueling station might be put together to provide hydrogen fuel at a large scale. Because hydrogen can be produced in a number of ways, the design of a hydrogen energy system is site-specific depending on the type of demand, local energy prices for natural gas, coal, electricity, etc., and the availability of primary resources. Clearly, a large variety of different hydrogen energy systems could be analyzed. Many of these systems, although locally important, would have limited application on a global energy scale. In the interests of space and keeping the reader's attention, we have restricted our discussion to what we see as potentially one of the most important applications: developing infrastructure to supply compressed hydrogen gas to zero-emissions vehicles. Compressed gas was chosen as the most likely near-term storage for hydrogen. See discussion of onboard vehicle storage options above. Further, we present a specific case study for Southern California, a location where hydrogen and fuel cell-powered vehicles are being demonstrated, and where a high degree of political will to implement cleaner transportation technologies is evident. Estimating the demand for hydrogen energy. The first step in designing a system to deliver hydrogen transportation fuel is characterizing the hydrogen demand to be served. Table 2 shows hydrogen consumption for various end uses, ranging from a single hydrogen fuel cell powered car through implementation of hydrogen in large energy markets. A single hydrogen fuel cell automobile driven 11,000 miles a year, the US average, is projected to use 109 SCF of H2 a day. Hydrogen fuel cell bus driven 50,000 miles a year is projected to use 8,000 SCF of H2 a day. The total number of vehicles to be served determines the total hydrogen production capacity needed. For example, to serve 10% of the automotive fleet in Los Angeles area, or 1 million cars, about 100 million SCF of H2 a day must be produced. Providing hydrogen for 36,000 urban transit buses, the estimated number in LA, would require about 25 million SCF a day. Either centralized or decentralized hydrogen supply could be used. A large chemical industry SMR today produces 25 to 100 million SCF a day, enough to serve 2.5 to 10% of the cars in LA. Hydrogen could be piped from a large central plant to users in local pipelines or liquefied and delivered by truck. Alternatively, small reformers or electrolyzers in the range of 0.1 million to 1 million SCF a day could be sited at individual refueling stations, each serving 60 to 600 cars a day. The geographical concentration of the demand, number of vehicles per square mile, is important for determining the type of distribution system and the cost of local distribution. As shown in Figure 7, local pipeline transmission costs vary from $2 a gigajoule for vehicle densities of 3,000 cars per square mile, equal to 100% of cars in densely populated urban areas such as downtown Denver or LA, to $5 a gigajoule for densities of 300 cars per square mile. Equivalently to more sparsely populated suburban areas, such as averages for New Jersey, or to 10% of urban vehicles. At even sparser demand concentrations of less than 300 cars a square mile, pipeline transmission costs rise rapidly, and other hydrogen supply strategies are preferable. The proximity of the demand to primary resources for hydrogen production is also important. This determines the most viable alternative by determining local energy prices. Selecting the lowest cost hydrogen supply option. General considerations. From the hydrogen production and delivery costs shown in Figures 4, 5, 6, and 7, we can make preliminary selection of least cost systems for a given level of demand and given energy prices. Where low-cost natural gas is available, the production cost is lowest from steam methane reforming, and over a wide range of production sizes, ranging from a large central system producing 100 million SCF of H2 a day to the size of a single hydrogen refueling station producing 0.1 to 1 million SCF a day. Let's look at figures. Okay, I can't look at figures. Okay. Hydrogen production in a centralized SMR is less costly than in small-scale distributed SMRs because natural gas feedback costs are lower at large plant than at a refueling station. Scale economies are important for conventional SMRs. However, if advanced small, low-cost fuel cell type reformers are developed, capital costs per kilowatt of hydrogen output would be similar for large and small SMR systems. However, hydrogen distribution costs from a central plant to users can be significant. Where natural gas is available, a key question is the degree of centralized fuel production. If distribution costs are high, decentralized production may be the lowest cost option. With coal and to a lesser extent biomass or waste, large-scale plants are favored because of scale economies in production equipment. However, biomass hydrogen plant size is limited by the cost of transporting biomass over a large distance. For gasification-based technologies, a large demand is needed to use the output of the plant, and a geographically concentrated demand is needed to keep local distribution pipeline costs low. Generally, biomass and coal gasifier systems will be competitive only where low-cost natural gas is not available and only when a large concentrated demand has developed. Development of low-cost, small gasifier systems could change this outlook. Electrolytic hydrogen can be produced over a wide range of scales, but can compete with other options only where off-peak electricity prices are low or where costs for other feedstocks are high. Estimating the delivered cost of hydrogen transportation fuel, a Southern California case study. Using figures 3, 4, 5, and 6, and 7, and specific information about energy prices and vehicle populations in Southern California, we have estimated the cost of different hydrogen supply options. Southern California was chosen as a case study because it's a region with severe air population problems and because the state of California has demonstrated political will to implement lower polluting transportation technologies. A number of near-term possibilities for producing and delivering compressed gaseous hydrogen transportation fuel can be considered, which use commercial or nearly commercial technologies for hydrogen production, storage, and distribution. For details on the design and economics of these systems, see several recent studies of hydrogen refueling infrastructure. Near-term hydrogen supply options include a hydrogen produced from natural gas in large centralized steam reforming plants and trucks delivered as liquid to refueling stations. B. Hydrogen produced in large centralized steam reforming plants and delivered via small-scale hydrogen gas pipelines to refueling stations. C. Hydrogen from chemical industry sources, e.g. excess capacity in refineries that have recently upgraded their hydrogen production capacity, etc., with pipeline delivery to fueling station. And D, hydrogen produced at the refueling station via small-scale steam reforming of natural gas in either conventional steam reformer or an advanced steam reformer of the type developed as part of fuel cell cogeneration systems. And E, hydrogen produced via small-scale water electrolysis at the refueling station. In the longer term, other centralized methods of hydrogen production might be used, including gasification of biomass, coal, or municipal solid waste or electrolysis powered by wind, solar energy, or nuclear power. Thermochemical hydrogen production systems might include sequestration of byproduct CO2. In Figure 10, we show the estimated delivered costs of hydrogen transportation fuel for Southern California. The delivered costs are shown for each technology. For refueling stations dispensing 1 million SCF a day, each station could fuel a total fleet of about 9,000 fuel cell powered cars or 140 fuel cell powered buses. Comparison shows the following significant results. More figures I will not look at. Delivered costs for hydrogen transportation fuel range from 11 to 25 dollars a gigajoule, equivalent to an energy basis of $1.60 to $3.80 a gallon of gasoline, depending on the technology. This is substantially more than untaxed gasoline. However, hydrogen can be used more efficiently than gasoline in a fuel cell car because gasoline incurs conversion losses in an onboard gasoline fuel processor, so the true fuel cost per kilometer can be comparable to current costs. For Southern California energy prices and resource availability, widespread availability of low-cost natural gas, on-site production of hydrogen via advanced small-scale steam reforming of natural gas is the lowest cost option and has the advantage that no hydrogen distribution system is required. Truck-delivered liquid hydrogen might also be attractive for early demonstration projects because the capital requirements for the refueling station would be relatively small, and no pipeline infrastructure development would be required. However, delivered fuel costs are higher because of the high cost of liquefaction. Under certain conditions, a local gas pipeline bringing centrally produced hydrogen to users could offer low delivered costs. Our example assumes that it costs $5 a gigajoule to produce hydrogen in a large SMR plant. Centrally produced hydrogen ranges from 3 for refinery access to 5 to 9 for large-scale steam reforming to 8 to 10 for hydrogen from biomass coal or municipal solid waste. Municipal solid waste. The cost of pipeline distribution is given two cases. A low-density case, in which a car population density of 3,000 cars a square mile, similar to the average vehicle density in the LA basin, or 10% of the city vehicle population density, is served. And a high-density case of 3,000 cars per square mile, similar to the vehicle population in the city center. For a small-scale hydrogen pipeline system to be economically competitive with on-site small streaming for forming, a high demand would be required. Alternatively, small demand might be served by a nearby low-cost supply of hydrogen. For example, a bus garage located near a hydrogen production plant. Heavens. On-site electrolysis would be more expensive than other options unless the cost of off-peak power let me deal with this madness. Just save some time and ban everybody who says trash. There we go. Spam gone. On-site electrolysis would be more expensive than other options unless the cost of off-peak power is very low. In Southern California, the cost of off-peak power is 0.3, not even that. It's about 3 cents a kilowatt hour, placing the cost of hydrogen well above that of on-site steam reforming. Figure 10. But an off-peak power cost of a penny a kilowatt hour, electrolysis competes with on-site steam reforming. Off-peak power is available in 1 penny a kilowatt hour in some locations, such as Brazil, which have excess off-peak hydropower. The amount of very low-cost off-peak power available in Brazil might fuel 1 million to 2 million hydrogen fuel cell automobiles. In this range of hydrogen demands at a refueling station, no one supplying option is favored under all conditions. For different energy prices and demands, the relative delivered hydrogen costs would be different. Capital costs of hydrogen infrastructure. The capital cost of hydrogen infrastructure is often cited as a showstopper for hydrogen vehicles. Figure 11, we showed the capital cost of building a hydrogen refueling infrastructure for the various options discussed above. We considered 2 levels of infrastructure development. As I said earlier, this is levels of infuriating to read, because this is not like the idea that investing in something new is bad and we shouldn't do it, because this is not just about transitioning to hydrogen. It's about transitioning off of fossil fuels, a thing that will kill all of us if we don't be more careful about it. Maybe I shouldn't say we'll kill all of us. We'll kill all of your grandchildren. Early development of a distribution system and refueling station to bring excess hydrogen from existing hydrogen capacity to users or produce it on site. We assume that no new centralized hydrogen production capacity is needed. 2 refueling stations serve a total fleet of 18,400 cars, each station dispensing 1 million SCF of H2 a day to 650 cars a day. Alternatively, this level of infrastructure development could serve 2 bus garages, each housing 140 hydrogen fuel cell buses. The option for providing hydrogen include A. Liquid hydrogen delivery vehicle. The options for providing hydrogen include A. Liquid hydrogen delivery via truck from existing hydrogen production capacity. B. Pipeline hydrogen delivery from a nearby large hydrogen plant or refinery. And C. On-site production from steam, reforming of natural gas, and D, on-site production from electrolysis. There's still a lot to go here, and I've got 10 minutes. That's not ideal. I will see what I can do in damage before I quit, I guess? No, it's just so much. Alright, I'm going to get to the environmental and safety considerations. Then I will have to go. That'll be over my time. So development of new hydrogen production, delivery, and refueling capacity to meet growing demands for hydrogen transportation fuel. The system serves a total fleet of 1.4 million cars with 153 fueling stations. Each station dispenses a million SCF of H2 a day to 650 cars a day. There are projected to be about 7.8 million cars in LA in 2010, so this case would be equivalent to a fleet of LA for which about 18% of the cars were hydrogen fuel cell powered vehicles. Options for providing hydrogen are a liquid hydrogen delivery truck from a new centralized steam reform, B, pipeline hydrogen delivered from a newly centralized hydrogen plant, and C, on-site production from steam, reforming of natural gas, and D, on-site production from electrolysis. A breakdown of hydrogen infrastructure capital costs is shown in Figure 11. For a large-scale system, a hydrogen steam reformer plant costs $100 million. A liquefier adds $200 million, plus $40 million for liquid hydrogen delivery trucks, and $140 million for refueling stations with liquid hydrogen delivery. Alternatively, hydrogen can be distributed as a gas. Hydrogen compressor at the central plant adds about $17 million and a half a day's storage to meet time-varying demands for fuel costs adds $50 million. The extent of the required pipeline system depends on the geographic concentration of the demand. For a low-density case with a vehicle population of 300 cars a square mile, the pipeline system consists of 10 spokes, each stretching 40 miles from the central plant. The capital cost of the pipeline is $385 million for the high-density case with 3,000 cars a square mile. Each spoke is only 12 miles long, and the total pipeline capital cost is $122 million. Refueling stations add $260 million for gaseous hydrogen delivery. Total capital cost is less with liquid hydrogen delivery than with gaseous hydrogen delivery. But the delivered fuel cost is higher for liquid hydrogen because of the high energy cost of liquefaction. The range of infrastructure capital costs for a system serving 18,400 fuel cars is about $1.4 million to $11.4 million, or $80 to $620 a car. $80 a car is for a liquid hydrogen truck delivery, including station costs only. No new production capacity or delivery trucks are included. The range of infrastructure capital costs for a system serving 1.4 million fuel cell cars is about $440 million to $870 million, or $310 to $620 a car. For advanced on-site stream reforming, the capital cost is about $516 million, or $370 a car. Okay, so for centralized production with pipeline delivery through a highly developed urban area such as LA, the capital cost of the hydrogen pipeline is assumed to be $1 million a mile and accounts for almost half of the total infrastructure capital costs. In a location with lower labor costs, the total pipeline cost might be reduced somewhat if the location is not as well developed, so the construction of the pipeline can avoid excessive road crossings and etc. Capital costs could also be reduced. As shown in Figure 3, large biomass or coal hydrogen plants would cost perhaps threefold as much as large SMR plants with the same hydrogen output. The overall capital requirement of a hydrogen infrastructure might be increased by 40%, as compared with a system based on centralized steam reforming of natural gas. Innovative technologies for gas separation might reduce the capital cost of gasifier plants. Hydrogen infrastructure capital costs compared to those of methane, gasoline, and synthetic middle distillates. How much does the capital costs of developing hydrogen refueling infrastructure compare with costs for other transportation fuels, such as methanol, gasoline, or synthetic middle distillates from natural gas? It's often stated that developing a hydrogen infrastructure is much more costly than developing infrastructure for liquid fuels. However, recent studies found that the off-vehicle infrastructure capital costs for hydrogen are similar to those for methanol or SMD once a high level of fuel use is achieved. This is shown in Figure 12, which compares infrastructure costs, including fuel production, fuel delivery, and refueling stations for hydrogen, and methanol and SMD in terms of capital costs for infrastructure per car served. Early infrastructure development, where no new fuel production capacity is needed, and large-scale infrastructure with production capacity are shown. Surprising result, because one would expect a liquid fuel-based infrastructure to be inherently less costly than one of gaseous fuel, even though the fuel distribution system is less costly for liquid fuels than for hydrogen. Fuel production plant costs are higher for methanol and SMD than for hydrogen, and moreover, hydrogen can be used about 50% more efficiently on board a vehicle than can methanol or SMD, so that the overall capital cost per car for fuel infrastructure is lower. Costs for maintaining or expanding the gas refueling infrastructure to meet future needs are also considerable, possibly several $100s per car served. Conventional wisdom that hydrogen infrastructure is much more capital intensive than methanol or gasoline is true only for small market penetrations of hydrogen or methanol vehicles. Once a large number of alternatively fueled vehicles are on the road, capital cost is large to develop any new fuel because new production capacity is costly. Moreover, zero-emissions fuel cell cars are using methanol, SMD, or gasoline are likely to be more expensive and less energy efficient than hydrogen fuel cars. If the concept of infrastructure is expanded to include hydrogen production equipment, fuel processors, onboard gasoline or methane fuel cell cars, we see that methanol vehicles are projected to cost $500 more per car and SMD vehicles $1,000 more per car than hydrogen vehicles. Hydrogen appears to have the lowest overall capital cost, including costs both on and off the vehicle. Comparing the costs or life cycle costs of automotive transportation. Comparing the delivered cost of hydrogen transportation fuel on an energy cost basis, dollars per gigajoule, we find that hydrogen is 50 to 100% more costly than gasoline. However, hydrogen can be used about 50% more efficiently in fuel cells than gasoline or other liquid fuels, so the fuel cost per kilometer traveled can be comparable. There are several reasons why hydrogen fuel cell vehicles are more energy efficient than fuel cell vehicles with onboard fuel processors. A, to achieve the same performance, vehicles with onboard fuel processors weigh more. B, fuel cells perform better on pure hydrogen than on reformed gasoline or methanol, which is a mixture of gases. And C, there are energy conversion losses in making hydrogen in fuel processors. Studies of the projected cost of hydrogen-fueled transportation have shown that if a fuel cell vehicle reached projected costs in mass production, the total life cycle cost of transportation, accounting for vehicle capital cost, operation and maintenance costs, and fuel costs, could be slightly less for hydrogen than for methanol or gasoline fuel cell vehicles. Projected capital cost of fuel cell vehicles as compared with competing internal combustion-based technologies, such as diesel, battery hybrids, are still uncertain, although fuel cells appear to be competitive to within the accuracy of projected costs. However, hydrogen does appear to have advantages over liquid fuels as a fuel for fuel cell vehicles. This one is interesting. This came out, the EU put a piece of paper out. And for short distances, batteries are better, and for longer distances, hydrogen is better. And I don't remember the breakdown, but it was pretty reasonable.